I'm very happy to be speaking here. When I found out I was going to be speaking in Lithuania here in particular, I was excited because my great-grandfather was born here. But I didn't know quite what to expect in terms of audience and your place technically. So when I told some of my peers I was going to be speaking here, they said, oh, well, you know, Eastern European, like they're going to have a different sense of humor, so don't tell any jokes, which is fine because I'm not a funny person, so I'm not going to tell any jokes. And I said, you know, just be clear and serious, and whatever you do, don't use any of that American sarcasm, which seems like very good advice. But I'm going to be talking about chaos engineering, so I don't feel like I have much of an incentive to take very good advice, especially for something that feels so intuitively true. So what's chaos engineering? Oh, I work at a company called Verica. I'm not going to talk about it. Chaos engineering started with a program called Chaos Monkey about 10 years ago, 11, maybe 12 years ago, at a company you might have heard of called Netflix. Small video streaming company. They don't carry much Disney stuff anymore, though. And so what Chaos Monkey does is it will pseudo-randomly select an instance from every service running in their microservice architecture once a day and turn that instance off. Why would they do that? That seems kind of counterproductive, right? Well, they did that because at the time they had just migrated out of the data center into the cloud. And they had several months of instability because one of the features of the cloud at that time was that instances would spontaneously disappear. Right? It was a feature from AWS. No warning, instances would just disappear. And so it turns out they had a lot of single points of failure and other things that would cause the system to come down when an instance would disappear. Now, if we were to sit in a room and come up with ways to build an architecture that's resilient to that, we could probably come up with a dozen different methods fairly easily, right? That wouldn't be difficult. But an interesting thing about Netflix, they don't have a CTO. They don't have a chief architect. They don't have a VP of engineering who sits over the entire software product. So even if they came up with those methods, there'd be no mechanism to force all of the engineers to do it. So they tried a couple of things. They tried many things to fix this availability issue. And the thing that worked was Chaos Monkey, because it took the problem that the business needed to solve and put it right in front of the engineers, very clearly defined. They couldn't get their work done, like at all, that week, unless they fixed this problem. And once they did fix this problem, then they didn't have to worry about it again. And so Netflix hasn't had an outage due to a single instance disappearing since. So they thought, okay, that worked really well at the small scale. What about at the large scale? The control plane is deployed for Netflix is deployed in 3 regions in AWS. And it turns out even just the control plane, like video streaming aside, the control plane is a lot of traffic. It's like 3% of internet traffic in North America. So that's quite large. So they balance it between these 3 regions. And not that this ever happens, but hypothetically, a region in AWS could go down. And so to make sure that the system is resilient to that, they built this thing called Chaos Kong, which would take a region down, take an AWS region down. Well, it wouldn't actually take a region down. Something about there being other customers on it. AWS wouldn't let them do that. So instead they simulate it, right? They simulate taking a region down frequently now, and the service stays up. So when an AWS region does get a little wonky, US East 1, they can keep the service up and running because they can move all of those customers easily to the other services, even with their microservice architecture. Okay, so it works well at the small scale, worked at the big scale. Now, what about in the middle? I'm going to be talking a lot about complex systems. So I just want to lay some groundwork for what I mean by complex system. This is it's on a loop. It's an animated GIF. But this is a GIF of Netflix's microservice architecture, the critical path for video streaming. The open circles are microservices. So this is traffic coming in from the internet, fanning out through the microservice architecture. The moving dots represent request responses. Blue means they're okay. Every once in a while you'll see a red one. That's like a 500. And so what I want you to get out of this image is the impression that this system is complex. And specifically by that I mean no human can mentally model all of the pieces of how this works. A human can't fit all of this in their brain. And practically speaking, each microservice is owned by a team. That team, hopefully, understands their microservice very well. And they probably have a good understanding of one up and one down, but that diminishes quickly after that. So the engineers working on this system don't even know how all of the pieces fit together. And in fact, Netflix doesn't have architects because it would be impossible. And because they've structured their organization differently so that they don't need architects. This system works even though no human can understand how a request response works from the time it comes in to the time it hits whatever these backend services are doing to when it's returned to the client. Okay, so that's a complex system. And if you're not working in a complex system yet, you will be soon if you stay in software. Because that's where everything's headed. So what could go wrong in a complex system? I'll give a couple examples. These are real stories that I've anonymized to protect the innocent. Very, very typical setup here, the snippet of a microservice architecture. So large enterprise company, they've got a bunch of services, A, B, Z, a bunch of microservices. So they stick an API layer in front of it, right? Very common. Of course, that's a single point of failure, and it's taking a lot of traffic, so they horizontally scale it. They run it on a bunch of instances. But it's a custom API service that they wrote in-house, and they build a self-service tool in front of it so that everybody in the company can write their own rules to like match on URLs and do different things and enrich requests and eventually identities in there and security and all these other features. And the app grows and grows and grows. And it's written in Java, which means that these services end up being really big. In fact, they get to the point where they're so big that it takes about 40 minutes from the time you want to request a new instance to the time that it's up and running in steady state. By the time AWS provisions the instance and the OS boots and Java VM initializes and gets all of its memory and downloads stuff, it takes a while. In this company, does anybody here do code freezes? Like before holidays? Seeing a couple of heads shake. Okay, so this company had it was a online retail thing. So for them, Black Friday, Cyber Monday was a huge spike in traffic and very critical to their business. So they go, okay, in order to make sure that we're stable, we're going to initiate a code freeze the month before. So they've got a little more than a month before big business. So 2 weeks after the beginning of the code freeze, they start getting errors on one of these instances. And the errors increase, and they don't really know what the problem is, and they can't do much about it, so they reboot it. They take it down, and they boot another instance in there. Now, the whole service is over-provisioned by 50%, right? So it can handle a third of these going down, and it should still be able to handle traffic. But as they're rebooting that, errors start accumulating on the other servers in this cluster. And eventually it affects the whole cluster. And so through this process of bringing up new instances, takes 40 minutes per instance, and trying to figure out what's going wrong with the old instances, they've got like 4 to 6 hours of degraded service. Fortunately, again, this is like well before Cyber Monday. But it's during their code freeze. But they can't figure out what the problem is. So now, what do? You've got a code freeze. You don't want to change the code because you've got a code freeze. So how do you figure out what the problem is? They decided, this happened on a Friday, they decided, okay, on Monday, we're just going to take a small number of servers in the cluster, add some instrumentation, some more observability, and then reboot those. So just a small number of servers will have different code. Another 2 weeks goes by, and the same thing starts happening. Errors increase on one instance, then two, and eventually it affects the whole cluster, except for the instances that they added instrumentation to. Except 3 days later, that one goes down as well. And then they find out that they have a memory leak. And so they look into it, and basically they have memory was being used geometrically corresponding to the number of requests coming in, and because they had good load balancing in front of this, they all got about the same number of requests. So they all ran out of memory at about the same time. And the package that had introduced the memory leak had been brought in the previous February, right? This is less than a month before the holidays. It's around now time, this time of year. And the previous February, this dependency had been introduced with a memory leak. They had never run into it before because they were always adding new features. So they were redeploying every day or two. So the code freeze that they initiated to make the system more stable brought down the system. Give me another one. So this is great. I love this example because sometimes people ask me, hey, can we do chaos engineering in staging, or is it only for production? No, you can absolutely start it in staging. The gold bar is that you do chaos engineering in production, but start where you're comfortable. So this one company, again, this was also a retail company, dipped their toe in the water for chaos engineering with a game day. So they got everybody in a war room, and they planned this out beforehand. They said, okay, we've heard a lot about Kafka going down, instabilities in Kafka. So we're going to make sure we're resilient to Kafka going down. And they have this staging setup that's an exact clone of their production setup, right? Stateless services throw stuff on Kafka, and that pushes out to push notifications to mobile and logging and billing. And they have a pretty clear expectation of what's going to happen here. If they take Kafka out in staging, in particular, they were looking at logging. Logging should stop working, but the site should stay up, right? So everybody's in a war room. They're going to try this out on staging. They remove staging, and sure enough, those three things stop working. And the staging site stays up, but production immediately goes down. Turns out they accidentally had one of these. And how they ended up with this is a really interesting story. They started off with one Kafka cluster, right, in development, and as they built, as they scaled out and they moved up, they built a new, bigger Kafka cluster for production. But one of the configs that pointed the site, as it gets promoted from staging to production, wasn't set to push the logs from the staging Kafka to the production Kafka cluster. So what I love about this is, if you took everybody, all of those engineers, really smart engineers, and put them in a room and said, tell me all of the things that could possibly go wrong, they wouldn't come up with this, because this is knowledge that they wouldn't have. They wouldn't think of this. And yet we could all end up there. So when production couldn't hit that Kafka cluster, it basically ran into thread pool exhaustion, and those applications stopped responding. One more example, because I love the failure stories. So here's a snippet of a microservice architecture. Again, it's a commercial retail thing. So information comes into microservice, we'll just call it P, that has let's say personalization data, right? So stuff about people. And it basically wants to store that information with some metadata, picture like an ID and a bunch of metadata, and it says, okay, I want to persist that, and then I want to retrieve it, and it's always in that loop. Like, you're never deleting people, you're always just like adding to it. It's monotonically increasing. And so it sends that information to the service queue that persists stuff. And the team that runs queue persists that in two places. A columnar or data store, we'll say Cassandra, and Redis for a cache, a faster cache for lookup. And really good engineering teams, so they have a bunch of failover code in here, a bunch of great, robust design properties. So like P in its fallback says, okay, if for some reason I get an error or can't talk to Q, I'm just going to return a default experience, right? Like something about like people in general, even if it doesn't have their metadata. And Q does the same thing. It says, okay, if I can't talk to Cassandra, if I can't talk to Redis, I'll get stuff from Cassandra. And if I can't get it from Cassandra, I'll return a default piece of data or default response. And it generally reads out this way. So again, I'm not saying this ever happens to anybody else, but for some reason, in this case, Redis went down. Has that ever happened to anybody here? No, right? So Redis goes down. This is fairly typical. When you have a read-heavy use case, you put a cache in front of it, you utilize that cache, and you lose all sense of how much traffic the persistent data store can actually handle. And so that happened here too. Cassandra quickly got overwhelmed with the requests coming out, even though it could handle very well read requests that match the write request speed of stuff going in. Turns out that the read request rate had exceeded the write response rate by several factors, right? So a lot more traffic than it can handle. Cassandra slows down, eventually stops responding, like my mouse. So now Q has that fallback, and it says, okay, if I can't talk to either data store, then I'll return a default response. And in this version of Cassandra, when it can't get a quorum, it returns a 404. So Q returns a 404 to P, except P never deletes people. So it gets the 404 and says, WTF. And takes the whole service down. So this was a mismatch between an infrastructure level decision and a business logic decision. And again, if you took both of these teams and stuck them in a room and had them like figure out all the things that could possibly go wrong, I don't think they would think of this, because it's never going to cross the minds of the engineers on team P that data that they sent in that they know is there can't come back. And it makes perfect sense from Q's point of view that they would return a 404 if they can't talk to Cassandra, because that's what Cassandra does if it doesn't have a quorum. So these examples are fascinating to me because all components could be 100% correct, and yet the system exhibits undesirable behavior. And that's generally what chaos engineering seeks to address. So how do we survive these undesirable effects of complex systems? Or an easier way to ask this is, how do we make systems reliable? There's this model by someone named Hans Rasmussen, where you have three pillars, right? Economic, workload, and safety. And imagine you're in the center and you've got rubber bands that attach you to these three pillars. And so if you stray too far from one of the pillars, the rubber band snaps and it's game over for you. Okay, implicitly, engineers operate within this triad. So economic, right? You probably do not have a rule that when somebody's onboarded, you sit them down and say, now, okay, you are not allowed to spin up 100 million instances on AWS, right? Why don't you have to give people that rule? Implicitly, everybody knows that they have a cost, resource cost, and if you exceed the costs, like your business is going to die and it's game over, right? So you don't have to tell people that. The same is true of workload. If you don't have to tell engineers, you can't plan to do 200 hours of work in 1 week, like you're just going to exceed your workload. And the same with servers. Does anybody have engineers that do that? Occasionally it happens. But like seriously, like that you don't want to burn out, your team doesn't want to burn out, you can't burn out your servers, they've got physical limitations on how much work they can handle, so you don't have to tell them that. They implicitly operate within those boundaries. The same is true of safety, but here's the difference between safety and workload and economics. You have no intuition of how close you are to snapping that rubber band between you and safety. And I'm comfortable making that generalization because you all probably still have incidents. And if you knew that you were going to have an availability outage or a security incident tomorrow, you'd probably stop what you're doing and fix that so it doesn't happen. The reason those things happen is because we don't know they're about to happen. We don't have a good intuition for those being right around the corner. So that's the model that chaos engineering is based on. It goes, okay, if we can give engineers an intuition for how close they are to that safety margin, how big that safety margin is, how close they are to snapping that relationship with the safety of their system, then we won't have to tell them to be safer. They will just do that implicitly. So how does chaos engineering do that? Well, it builds tools that facilitate experiments to uncover systemic weaknesses. So you run experiments, usually on a live system. Again, the gold standard is to run these out in production, that figure out where those vulnerabilities are and feed that information back to the engineers so that they know, like, oh, okay, when this happens, customers have a bad time. And they know that's bad. So you don't have to tell them, like, okay, that means you have to do work here. They will just implicitly change how they go about engineering their part of the product. So that's where chaos engineering is. I want to talk a little bit about where it's going. Yesterday I was giving a talk in Germany, and I'm not saying this is true, but I'm gonna generalize a stereotype that Americans have about German engineers. Americans think that German engineering happens in this way where like they sit down and plan everything a lot, and then when everything's like right in theory, then they make it and it just works. Whereas Americans see themselves as just like banging on a thing, getting it wrong, but a little bit closer to working right, and then eventually, hopefully it works. I don't know if that's true, but like, so a lot of Americans are like, oh, if we were better engineers, we could be more like the way Germans build stuff. It turns out neither of those models are actually particularly good for knowledge work. Here's one way to think about navigating the complexity of the systems that we're working on. I call this theory economic pillars of complexity. I call it that because I stole it from Kent Beck, who stole it from an economics person, and Kent didn't have a name for it, so I just gave it this name. So there's 4 pillars in this model: states, relationships, environment, and reversibility. And the quintessential example from the literature for this model is Ford, the motor company, in 1913. So very complex manufacturing process, product market at the time. So what did Ford do? First thing he did was he controlled the states of the product and manufacturing. He said you can have whatever kind of car you want as long as it's a black Model T. And all the parts were standardized. That made the manufacturing process, helped him navigate a complex manufacturing process. Same with relationships. So he borrowed from Taylorism, created what he calls scientific management, and said, okay, other car companies had teams that built cars from the ground up. Ford adopted assembly line manufacturing and basically said, like, you know, that an assembly line engineer, manufacturer could talk to the person on the right, probably not even the person on the left. So he drastically limited the number of relationships between parts and tools and people. And that helped him navigate a complex manufacturing process. Environment. So not many people remember this, but Ford broke up the American motor monopoly, and then they eventually kind of became a monopoly. So they were able to affect their environment by basically changing the laws to make it more amenable to their line of business. And then reversibility. This is the one thing that Ford couldn't really control, because Model Ts, you couldn't really disassemble them and undo a mistake. Okay, so that's how the model's usually used. How does this work in software? Well, chances are you don't have much control over the states of your software, because there's a business imperative to constantly increase the states, right? And I'm not just talking about the data, but all of the functionality. That you're probably paid to add state. You're also probably going to add relationships, and everything from the stuff running underneath your systems. Now we've got containers and maybe serverless stuff underneath there, the relationships with that, plus microservices that explicitly increases the relationships between the moving parts. So that's also increasing. So software doesn't really get that benefit in navigating complex systems. Environment, you probably can't control unless you're a monopoly, Amazon. So that brings us to reversibility. This is where software excels. So obviously software, not hardware, so there's an amount of reversibility in that. But about 20 years ago, XP in particular introduced a more sophisticated form of reversibility in the engineering process. Waterfall, you build something for a year, put it in front of a customer, they go, I don't like it. You say, tough, you have to live with it. We can't undo a year's worth of development. XP said, okay, we're going to break that into very small segments, say like a week or 2 weeks, put it in front of the customer, and they say, no, that's terrible. Fine, we can throw that away. Here's another iteration. That's a little bit better. Okay, throw that away. Here's another iteration. By the third time, you're probably kind of tracking what the customer wants or what they're going to pay for. Okay, that's a process change that improves reversibility. But in the past 10 years, we've had a bunch of tooling, engineering, design decision changes that improve reversibility. Can anybody think of any? No? Anything that improves your reversibility? Say that again? Source code repositories, yes. Git, SVN before that, or source code control, but also the things that help us get code into production and back out faster. So CI, CD, automated canaries, feature flags, containers, anything that helps the developers get their code into production faster, realize they made a mistake, and get it out of production or roll forward. So what's great about this is architecturally, we can make design decisions now that improve the reversibility of our complex systems, that will make it easier, it'll pay dividends, it'll make it easier for us to maintain those systems going into the future. Okay, that's the kind of thing that we need to optimize for, and we're on the verge of doing that. So we could say that software engineering, the reversibility profession. That doesn't really make a catchy t-shirt though, does it? So let me share, I apologize for putting this block of text up in front of you, but the chief merit of software engineering is its technical efficiency with a premium placed on precision, speed, expert control, continuity, discretion, and optimal returns on input. Does that sound right? No? Oh man, the German audience yesterday loved this. They're like, yeah, absolutely. Except I accidentally did this. Here's the real quote. Chief merit of bureaucracy. But a lot of engineers would agree with that previous statement. In fact, a lot of sociologists call software engineering the bureaucratic profession. I don't know if you, like in the US, that word has a very negative connotation. So sometimes I put this slide up and the audience is like, boo. Like, why are sociologists picking on us? Why would they call us something so terrible? No other industry does a better job of separating who decides what work to do from who decides how to do the work from the people who actually do the work than software engineering. And that's the chief merit of a bureaucracy. And in fact, that's the system that most companies in the United States anyway aspire towards for their software engineering teams, right? So people managers, product managers, project managers, tech leads, architects, all of those people exist to take responsibility away from the person doing the actual work. And that's wrong. It works great for assembling cars, which is why we do this in the software industry, is because we stole this, we borrowed this, it just evolved from engineering, from scientific management, and from Taylorism in the 1910s. It makes sense if you have, quote, a dumb mule who's assembling parts on an assembly line. You don't want them to change anything because they'll mess up the design, right? It's the exact opposite for knowledge work. So most of us operate in this model that just is a very poor fit for complex systems and for software in general. So we've got a lot of work to do. I want to mention a couple of myths. Again, these are the things that we have to overcome in order to have safer systems. By safety, I mean availability or security. First myth, if we remove the people who cause accidents, we can make our system safer. A lot of people think this. In the literature, it's called the bad apples method of management. If you just find the bad apples, like, oh, Joe, he's always there when the server goes down. And because of that geographic coincidence, clearly he's somehow correlated with that. And if we get rid of him, then the outages will go away. A lot of people believe this is true. Fortunately, we have a lot of data from the medical field that shows that, because hospitals tried this, right? Like, oh, they're associated with all of these malpractice cases. If we get rid of them, the malpractice cases will go away. No, actually, a lot of those people happen to be close to those malpractice cases because they were attracted to the worst problems, the hardest problems. And so the danger and the poor outcomes didn't change when you got rid of the people who had the most experience dealing with those poor outcomes. And this is true in software. Myth 2, if you just document best practices in runbooks, you can materially improve the availability of your system or the safety of your system. A lot of people put a lot of time and resources into this. It's fine, but with complex systems, they tend to fail in ways that you hadn't predicted previously. So, knock yourself out, but that's probably time and energy that could better be spent doing something else to improve availability or security. Third myth, if you just defend against prior root causes, right? Find all the root causes and then make those impossible, and you'll improve the availability of your system or the security of your system in the future. A lot of things wrong with this, even though intuitively it feels like this makes sense, right? The biggest problem with this is that root cause isn't a thing in complex systems. Does anybody disagree? Cool. One person, really? Root cause is not a thing. Root cause analysis is at best a waste of your time. Is it contentious for anybody? Good. I hope there are some questions that brought that. So RCA is a waste of time. Root cause is not really a thing in a complex system. So trying to defend against those is an investment in time that's not going to meaningfully improve your system safety. The other one is, if we just enforce the procedures, no, chances are the people who are designing the procedures don't really understand how work is done in practice. So that tends to not help. Avoid risk. I love this one because I hear this a lot in enterprises. Let's put guardrails up. Do you have that phrase here? We need to build guardrails. People are doing things that are too risky. If we build guardrails, they won't do risky things, and then the system will perform better. Does that happen here? Any analog for that language? Again, that intuitively makes sense. Turns out it's empirically wrong for a couple of reasons. One is we can't fundamentally transfer knowledge for how to operate a safe system to another human being. You have to build up that experience. So if you install guardrails, what you're doing is you're preventing your team from acquiring the experience that allows them to prevent accidents. Because chances are you have many, many more almost accidents that your operators prevent from happening than you have actual accidents. And every almost accident is everybody involved is getting a little bit more context on how to avoid the next one. And so guardrails prevent that method of learning. They also tend to get in people's way when they want to actually remediate something. So like one I commonly see is like, oh, we'll make sure nobody has SSH access, right? That way we'll just force it so that nobody can do this risky thing of SSHing into a machine. And then something goes down, and like the first thing that the experienced people want to do oftentimes is SSH into the box so they can see what the hell's going on, and they can't because there's guardrails in place. So even though it intuitively makes sense, it doesn't work. The other is simplify, right? The problem with these complex systems is that they're complex. So to solve that, we'll just take the complexity out and make them simple. A lot of things wrong with that line of thinking. But the biggest one is that it's impossible. And again, I can tell you why it's impossible. I can even give you some good thought experiments to prove that it's impossible. But I'll just leave you with this. Empirically, we know that success corresponds with your ability to navigate complexity. So if you deplete your complexity, you're going to have less success. And your business probably won't like that. And the seventh one, and I'll end with the miss here, add redundancy. I hear this a lot, like, oh, well, we just need to, we add redundancy or redundant functional pattern. And it turns out that redundancy that actually does not correlate with better system properties in terms of availability. In fact, some of my favorite failure stories are one of the biggest contributing factors is the fact that there is redundancy there. My favorite example comes from outside of software engineering, the Challenger explosion. An easier one to explain is Black Hawk helicopters. In the US military, they've got a motor that runs the rotor. I don't know much about helicopters, but that motor, because that can burn out, that can fail, they don't want to leave soldiers out in the field, it has a backup motor, right? Except the pilots know this, so they run the Black Hawk helicopters faster and further than spec and end up blowing out both motors. They'd be a lot more careful if there were only one motor, and so they'd have fewer of that type of accident. The example I showed before with the Redis was kind of acting as redundancy to Cassandra is a great example of how redundancy actually contributed to the accident by removing a signal people had for an impending disaster. So don't fight complexity is basically the theme of where chaos engineering has to take us as an industry. Instead, we have to learn to navigate it better. And here's what that looks like from an enterprise point of view. CI helped us improve availability and properties we wanted to optimize for by getting everybody's code together faster, because I generate bugs at a certain rate, you generate bugs at a certain rate. Separated, that rate is bigger than if we merge our code base. The merged code basically accumulates bugs at about the same rate. So the faster you get code together, the fewer bugs you have, right? That's the theory and practice behind CI. CD, you get that code into production faster, be able to undo it faster, gives you a tighter feedback loop, but also improves your reversibility. So it's architecting for better properties that way. Most enterprises in the US that I talk to have CI in place. Most have CD or are in the process of building CD into their workflow. And they're just now starting to talk about CV. Okay, once the system is already up there, once the complex system is already up there and running, how do we make sure that the system gives us the output that we expect, that we want? How do we continuously verify at the boundary the output of the system? And so here's another way to think of it. What we've been doing is along the bottom, reactive testing methodologies that validate known properties. What we're moving towards in continuous verification are proactive experimentation tooling that verifies system behaviors. And it's not that the things on the bottom are bad, it's just that those work better for not complex systems. And now we need the things on top to handle our increasingly complex systems, particularly at scale, and with the often life-critical things that are running on top of those. By life-critical, of course, I mean like Instagram. So tools don't create reliability, humans do. But tools can help. If you're interested in this stuff, Nora Jones and I wrote a book on it. We've got another book coming out in the beginning of the next year. And if we have time, I'd love to take questions.